Hello everyone, my name is Nabaruna Karmakar and I will be talking to you about a project we did with Boston Public Schools as part of SAS's Data for Good initiative. The problem deals with optimally assigning monitors or supervisors to accompany students with disabilities on school buses. There are several rules which need to be maintained while assigning monitors to students, with a goal of maximizing the number of routes within each monitor's package. For a given academic year, BPS manages 625 buses which go on 3,500 routes. On these routes are around 1,350 students who need monitors assigned to them. Each bus typically has 3 to 4 routes, each in the morning and in the afternoon, some of which require monitors. In the morning, the bus starts out from a yard, then picks up students from their homes and drops them off at their schools, then return back to the bus yard. In the afternoon, they start out from a yard again, pick up the students from their schools and drop them off at their homes, returning back to the yard. As roughly 40% of trips have monitors, a particular bus may have some trips with monitors and some without any. The goal is to build packages shown on the right for monitors to bid on at the start of each school year. Each package can typically have 2 to 7 routes or runs in it, comprising a mix of AM and PM runs. Only monitors who have 6 or more runs receive health insurance. Hence, it is beneficial to create these monitor packages in such a manner that maximizes the number of students supervised by one monitor as long as all student needs are met. After exhausting options in which the monitor stays on the same bus, they can be made to switch buses at schools, or they can stay on the bus to make connections. Building the packages manually takes anywhere between 1 to 2 weeks. Also, each individual package needs to be printed on separate sheets of paper, which further necessitates automation. SAS optimization was used to develop a mixed integer linear programming model, or a MILP model, to maximize the number of routes within a package while ensuring full coverage. Let's talk about some of the rules related to the type of monitors. Some students need either their own monitor, a 1:1 monitor, or can share a monitor with other students, a general monitor. For most students, there is no specific requirement that a specific monitor be assigned to them. Hence, a regular monitor can supervise all students who do not need special monitors, and they need to arrive and leave from the same bus yard in the morning and in the afternoon. It is sometimes required for students to be assigned to a specific monitor. That is, a student A has to be assigned a monitor X. These are special monitors, and the bus yards do not need to be the same in the morning and in the afternoon for them. Specific monitor individuals are sometimes designed for a particular student. Example, a paraprofessional at the school. These paraprofessional monitors are required to accompany the student during school hours. For them too, the bus yards do not need to be the same in the morning and in the afternoon. Let's talk about our first approach. We started out with a simple MILP model where, given a set of monitors, we tried to assign them to the routes requiring monitors. This was a very straightforward approach to solving the problem. However, it uses millions of variables and constraints, which makes the model not scalable. It did not take advantage of the underlying network structure of the problem. Our second approach was a simple network flow model with the schools and the bus yards as nodes and the bus routes connecting them as arcs. Since this model also had a large number of constraints and variables, a binary search method was used for faster convergence to the optimal solution. This model was able to solve a smaller instance, that is for the summer schedule, but could not be scaled to the whole year schedule. Finally, we came up with an integer multi-commodity network flow model with the bus routes as nodes and the set of feasible connections as arcs. The monitors were considered as the commodity flowing on the arcs, the special monitors were treated as binary commodities, while the regular monitors were treated as integer commodities. The objective was to minimize the number of monitors needed or the total number of packages, which in turn maximizes the number of routes within a package. This approach did not require to have the feasible set of monitors, but instead found the minimum number of monitors. To find the individual packages, the optimal solution from the MILP was decomposed into directed cycles using SAS network solver. So the current method of manually creating these packages takes about 1 week, while the SAS optimization model can solve in 20 minutes. We also use the SAS output delivery system to automate the printing of the packages on separate sheets of paper. We are currently in the process of validating the output of our optimization model on anonymized data and adding more capabilities like maintaining the student-to-monitor relationship over weekdays and minimizing bus transfers. That was my presentation. Please feel free to contact me with questions. Thank you.